Okay, girls, so we're going to start a new chapter today. I'm continuing with probability. It's called Discrete Probability Distribution. Okay, so this will be our last chapter before we end the Year 11 course. Okay, if you roll a dice, you can obviously get the numbers 1, 2, 3, 4, 5, 6. The number of times you observe a certain outcome, such as the number 1 or 2 on a dice, is random variable. Okay, and in Year 11, we're going to specifically look at discrete random variable, and that is just basically where the outcome can only be measured in whole numbers. Okay, so for example, rolling a die can only get like whole numbers 1, 2, 3, 4, 5, 6. Number of children in a family can only have like a certain countable number of children, not like 1.5 children. Okay, whereas in Year 12 you'll be looking at continuous random variable, and those are outcomes that can be measured in any units, such as the height, any continuous numbers where that involves decimal numbers. Okay, so we're going to be focusing on discrete random variable. Okay, now, so as I said, capital letter X represents the number of times a certain outcome is observed. So capital P of X means probability of an observed outcome, and this little x is the specific outcome. Okay, we'll get into that more in detail with an example. Now this can be also represented by just P of X. Okay, we'll get into that later. Let's have a look at example 3a to start off with. So it says in a random experiment, a die was rolled and the results recorded in the table. So as you can see, the number 1 was rolled 18 times, 2 was rolled 23 times, and so on. First question to start off with, how many times was the dice rolled? Well, obviously you just got to add all the frequencies, so 18 plus 23 all the way down to 22. If you do that, the dice was rolled 120 times. Okay? Now, it says draw up a probability distribution for this experiment. When it says draw a probability distribution, it means draw up a table like this, okay? Where X represents the outcomes that you can get. So that's the numbers 1, 2, 3, 4, 5, 6. And the probability of each outcome in that experiment, we can see from the table, the number 1 was rolled 18 times out of 120 times, okay? So that's what you write underneath here. So let me just go on, 23 out of 120. Also make sure once you've written them down, write down the simplified fraction. So put it in your calculator, okay? So this is what you call your probability distribution. They can also say draw up a probability function, all right? Now, question B, I'd like you to pay attention to the wording of this question. It says write the probability function or distribution, remember they mean the same thing, of rolling a die as a set of ordered pairs, bracket X, bracket that. Okay, now in this question, it says write the probability function of rolling a die. It doesn't say write the probability function of rolling a die in this experiment. There's a difference. So in this question, they don't want you to draw a table. They want you to express every single one of these as like a coordinate in a bracket. So what they mean is for the number 1 that was rolled, we're not going to write the experimental probability. It doesn't say experiment. It says write the probability function of rolling a die. That's it. That means write the theoretical probability of rolling a die, which in this case is 1 over 6 to roll a 1. And you have to do that for the rest of the numbers. So 2, you can obviously get 1 over 6 as well. I'll just write them all out. 3, you can also get 1 over 6. Okay, so yeah, so probability distribution doesn't always have to be a table. It usually is, unless they specify. It can also come as a set of coordinates. Okay? Right. Let's have a look at C now. Okay, so this is like a new question. It's not based on the same table anymore. A probability function for discrete random variable X is given by that. So it's actually defined. So probability of, in this case, getting a 0 or 2, let's say these are numbers represented on a die, can be represented by that function, okay? If you get a 3 or a 4, the probability is by substituting the numbers in here, and the probability is 0 for any other values. So they want you to draw a completed discrete probability distribution table, okay? So basically draw the same thing as what I've drawn there. That. Now, it's got 0, 2, 3, 4, and any other x values. That means all the values in between 0 to 4, okay? So 0, 1, okay? Now the probability of getting 0, you're going to substitute this 0 in replacement of here. So that means that's 1 over 16 4 minus 0. If you put that in the calculator, okay. Same thing, 1. 1 is not here, so it's any other x values, and it says that probability is just 0. Okay. 2 is here. If I substitute 2 in here, that's 1 over 16. 4 minus 2. 3. Put that in here. So 2 over 8, which is a quarter. And you get the idea. Okay. So this is how you read that and translate it onto a table. Next question. Find the sum of all probabilities. That just means add all of these numbers. Okay. Oops, sorry. Okay. You'll find that it always equals to 1. Okay. And I'll get into that later on. Part I. It says evaluate P of X if the numbers are odd. So what are the odd numbers here? We've got 1 and 3. So that just means add 0 and 1 over 4. Okay. And similarly, for IV, evaluate for all numbers less than or equal to 3. So that means add all these numbers up until 3. Okay? So this is how you work around and use probability distribution table. Alright? Let's have a look at example 5. Now before I move on, properties of discrete probability distributions, all values of x, so the observed outcome, must be mutually exclusive. So remember, mutually exclusive means two things cannot occur at the same time. So obviously if you roll a 1, you can't roll a number 2 on the same die at the same time. Yeah? And the sum of all probabilities has to equal to 1, which we already know. And the probability must always be an expression between 0 to 1, which you already know as well. This second property is the one that we'll be using most of the time. So let's have a look over here. Example 5a. A function is given by that. So this is the expression for any probability, given that the numbers are, or the outcomes that you can get is 1, 2, or 3. Is this probability function, is the function of probability distribution? Okay, so what you have to do is you have to find the values of each and every one of these probabilities. Okay, so if I substitute P1, that's just 1 over 1 over 3. That's 0. Now let's find the same thing for 2. So that's 2 minus 1 over 3. That's 1 over 3. And for P3, that's 3 minus 1 over 3. That's 2 over 3. So what you have to do is now add these numbers. Okay? So 0 plus 1 over 3 plus 2 over 3. And that does equal to 1. And because it's equal to 1, it is a discrete probability distribution. Okay? That's all it is. Question B. Now we're going backwards. Find the value of n given this table. So given this is a discrete probability distribution, find n. So in other words, all these probabilities, if you add them up, must equal to 1. So it's just equations, okay? So put all of this part in the calculator, and if you do that, you're going to get 9 out of 12 plus n equals to 1. So that means n is just equal to 1, take away that, which is 1 over 4. Okay, so this is the use of discrete probability property. Okay, the next property is uniform probability distribution. Okay, that's a case when every single one of your px values are the same. So for example, example 7a, it says which probability distribution is uniform? The number of heads when tossing a coin. All right, I like to draw up a table once again. Okay. When you toss a coin, you can obviously get heads or tails, but we're just focusing on heads here. How many heads can you get when you toss a coin? It's not just 1. You can also get 0 heads, correct? So these are the values that go in x. Now the probability of getting 0 head in a coin is a half, because that means you're getting a tail. And the probability of you getting a head is also half. So as you can see, because they're the same, this is a uniform probability distribution. Okay? However, example 7b, the number of heads when tossing 2 coins. So I'm going to introduce this now. You need to draw a tree diagram when there's more than one objects or more than one selection involved. So let's draw a tree diagram. So on our first coin, we can get head or tail. So back to our basic tree diagram. Okay. And let's write the outcomes. And let's draw a probability distribution out of this. How many heads can you get when you when you toss 2 coins? We can get 2 heads, 1 head, or 0 heads. So those are the numbers that would come in here. Okay, so the probability of getting 0 heads is this one, which is obviously 1 out of the 4 outcomes. The probability of getting 1 head would be this one plus this one, which is 2 over 4, which is a half. And probability of getting 2 heads is just 1 out of 4. As you can see, these are different numbers. Okay, they're not all the same. So this would not, whereas here, they're the same. All right. Okay, let's have a look at example 8. Draw a probability distribution table for the number of black balls that could be drawn out of a bag. So we're focusing on the number of black balls containing 5 black and 3 white balls when 2 balls are selected randomly without replacement. So we need to draw a probability distribution table for that scenario, okay? The way to know if we need to draw a tree diagram or not, like I said, it says 2 balls are selected randomly without replacement. So you've got multi-stage event happening because there's more than one selection happening. So that's a tree diagram. So let's do that. So because we have black and white, so there'll be 2 branches to start off with. So that's black and white. And obviously because there are 5 black, then it will be out of 8. 5 plus 3, then that would be 3 out of 8. And then, so that's my first pick. Second pick, without replacement, if I chose black, then obviously here I would have 4 black now, but out of 7 because I've taken 1 out. Okay, so we've got that. Okay, so I've got these numbers now. Now let's draw up the table. As you can see from here, there is a situation where I can get 0 black balls, okay? 1 black ball and 2 black balls will be my maximum numbers, okay? So for 0 black balls, there'll be this one because you're getting double white. 1 black ball would be this one plus this one, so that plus that, which is 30 out of 56. Simplified is, yep, okay? So this is how you complete a probability distribution table using tree diagram. Okay, let's have a look at another situation. Let's have a look at question 15 from your exercise. It says a company makes washing machines. On average, there are 3 faulty machines made for every 1,000 machines. 2 washing machines are selected at random for a quality control inspection. So because it says 2 washing machines are selected, that's a tree diagram with 2 branches like I've drawn there. Okay, draw up a probability distribution. So we want to draw up a table where we've got faulty numbers here. So before we do that, let's draw up a tree diagram. We can have a machine being faulty and machine not faulty. Okay, so probability of having a faulty machine, it says on average there are 3 faulty machines made for every 3,000 machines. That's actually the number for the probability of having a faulty machine. So then the not faulty machine would be 1,000 take away 3, which is 997 over 1,000. Okay, that's our first pick. For our second pick, because it says 2 machines are chosen, we can have once again faulty, not faulty. All right, so once again, let's write down the outcomes. So as you can see here, we can have double faulty, so 2 faulty, 1 faulty, and none of them being faulty. So that's like your same numbers again. So for 0 faulty, that will be this times this. I'll leave that as an exercise, okay? You obviously know what to do from here. All right, so that's how you set the question up. Similarly for question 18, I'll just give you a guide. The probability of a traffic light showing green as a car approaches is 12%. Draw a probability distribution table for the number of green traffic lights approach when car passes 3 traffic lights. So 3 traffic lights, 3 branches. So I'll set it up for you. So you got green, not green for your first traffic light. And it says 12%, so I'm going to write it as a decimal. So that means this has to be 100 take away 12%, which is 88%. Okay, use those numbers for the rest. It doesn't change, okay? And do the same thing. 2 more questions as a guide. Question 10. In a game, each player rolls 2 dice. So as soon as you see the word 2 dice, unfortunately, you do need to draw this table up and use that, okay? So I've got one here for you to use. The game pays $1 if one of the numbers is a 6, $3 for double 6, $2 for any other double. There is no payout for other results. So keep that in mind. So that means $0, because that's obviously a number you can get as well. Draw a probability distribution table for the game payout. So you can either win nothing, you can win $1. Does it say $2 anywhere? Yes. And $3. Okay. So this is how you would set it up. And then using this table, get the probability. So for example, it says $3 for a double 6. So there's obviously only one out of the 36 outcomes. So, okay. $2 for any other double, count them up, fill it up. Okay. Now, question 12. Simon plays a game where he selects a card at random from 100 cards numbered 1 to 100. Okay. He wins $1 for selecting a number less than 20. So I wrote it down here. So he gets $1 if it's any numbers less than 20. $2 for numbers greater than 90. $3 for any number from 61 to 69 inclusive. So I put like an underline there. And $5 for any number between 41 to 50. All right. Create a probability distribution table for the random variable. Okay. So when there is a prize or a game that includes money involved, you always got to put $0 in the table as well. Okay. So I wanted to point that out. So we can get $0. Obviously, these numbers are easy to fill out. So obviously, all the numbers less than 20 would be 19 out of 100. Okay, so that's the number that would go in here. Any numbers bigger than 90, this is obviously 10 numbers. Once I have all these probabilities though, how would I calculate the probability of $0? That's basically then all other numbers besides these, isn't it? So the quickest way to calculate the rest of the other remaining numbers, to 100 take away 19, take away 10, take away 9, take away 10, if you do that. Alright guys, that should be plenty of examples and questions for you to be now able to get through all the exercise. I've written the exercise number there. Give that a go and just, let me know if you have any questions. Thanks.